Hello everyone, welcome back to Introduction to Semiconductor Devices. This is lecture 8 of week 3. So in the last lecture we were talking about the diffusion process, and we also looked at the current expressions for diffusion and the drift currents. And after that we looked at what happens to semiconductor band diagrams when you have an applied electric field, and also the case of non-uniform doping. We saw that there was a built-in field that is created within the semiconductor when you have a non-uniform doping. And we also looked at how to analyze band diagrams, right? So today we will move further and we will talk about one very important concept, which is known as non-equilibrium response. We have seen the equilibrium response many times so far. So if you have a intrinsic semiconductor, there is electron hole pair generation process that happens because of thermal energy, and you have the recombination process that happens because when you have a electron hole pairs, electrons in the conduction band and the holes in the valence band, it is possible that at some points you have electrons and holes at the same location physically, and then they can recombine. Essentially, the electron gets absorbed into the bond. Okay, so the electron hole pair is annihilated, and because of that, we have the intrinsic carrier density. So we've seen multiple times. We kept on emphasizing that N equal to P equal to Ni is essentially the intrinsic carrier density when electron and hole concentrations are same. Okay, and we sometimes denoted that by using a subscript 0 to indicate equilibrium. So when you have equilibrium, then the Fermi energy was at the middle of the band gap. Now, we also saw the cases of extrinsic semiconductors, wherein we tried to use doping, and what doping did was shift the equilibrium, right? It shifted the equilibrium, and therefore you have more electrons and less holes. Okay, so if you have an N-type dopant, let's say donor atoms, then we shift the Fermi level closer to the conduction band, and that is why in an extrinsic semiconductor, N was Nd, and P, let's say equilibrium density of electrons was Nd, the number of dopants, and P naught is basically Ni square divided by Nd. And we said that N naught into P naught equal to Ni square. So this is valid even for an extrinsic semiconductor in equilibrium. So we want to ask us a very important question. Let's say we are able to somehow identify each individual electron in the conduction band, and similarly each individual hole in the valence band. So we ask, are the electrons and holes frozen? Are the electrons and holes, I'll say frozen, okay? So essentially indicating that if you are able to identify a particular electron, will it always stay in the conduction band? A particular hole, will it always stay in the valence band? Okay, so are they frozen in their respective bands at equilibrium? That's a question we ask. Okay, since we said that the electron and hole concentrations are whatever given by these expressions, right? So does it mean that a particular electron is always going to be in a particular band? Well, the answer is no, it's not true. So equilibrium implies that the net electrons and net holes are going to be the same. Okay, so equilibrium is a dynamic process by which I mean that electron and hole pairs are continuously generated and simultaneously they're getting annihilated. So a particular electron and hole pair can annihilate at one point, and at a particular location in lattice, and at some other position in the lattice, a different electron hole pair could be generated. There is no way for us to know which electron is in which band. I mean, is it bound to the lattice or is it free to move about? We won't know that. Okay, equilibrium only means that the net electron and hole densities are going to be whatever is given by these expressions, okay, in equilibrium. So what does non-equilibrium mean? Okay, so basically whenever we disturb, right, non-equilibrium means, let's say we are disturbing the equilibrium. Okay, How can we disturb the equilibrium? We could apply an external stimulus. For example, if I apply electrical voltage to a particular semiconductor device, let's say, and somehow I'm able to introduce additional holes or additional electrons, we'll see that this is possible. Okay, so this becomes a non-equilibrium situation, right? So essentially, this is equilibrium is shifted by external stimulus. Well, this stimulus could be electrical or it could be optical. We have seen many times this one already. So if you shine photons, you're able to introduce electron hole pairs, which are going to be in excess of the existing equilibrium carrier density. So it's an external stimulus and we are taking the semiconductor out of equilibrium. Okay. So one of the properties or one of the ways to identify a non-equilibrium situation is when you have the product N times P greater than, or let's call it not equal to Ni square. Okay. So what this means is, we'll take an example and show you this. Okay. So this is how you can characterize. Whenever you have an equilibrium situation, you have N naught P naught equal to Ni square. And if you have a non-equilibrium situation, the NP product is not going to be Ni square. Okay. So let's see how this happens. Okay. So let's consider a N-type semiconductor. Okay. Let's say the doping basically is, we'll take an N-type semiconductor, let's say with doping density of 10 power 15 centimeter cube. This is the doping density. So we have N naught equal to P naught equal to, sorry, N naught equal to 10 power 15. Excuse me. So we take the semiconductor and we shine light. We turn on the light suddenly. Okay. And this light basically, light creates, let's assume 10 power 16 electron hole pairs. Okay, let's assume, okay, per second. I mean, you should also do it per second, but anyway, per second. Let's assume this. Okay, so for 1 second you turn on the light. So what happens? The rate at which the electron hole pairs are created is actually this. Okay, so let's say, and we started out with what? We started out with N naught of 10 power 15 and P naught of 10 power 5, right? By this point, you should be comfortable how to get this. So I'm assuming that Ni is 10 power 10, Ni equal to 10 power 10. This is enough for me to do the calculations for right now. Okay. So now when I shine my electron hole pairs, I'm saying that I'm introducing 10 power 16 electron hole pairs. Okay. So after a second, how many electron hole pairs would be there? And now N. Okay. Now I'll introduce N to denote non-equilibrium, the total carrier density. Okay. N is going to be 10 power 15, the equilibrium density, plus delta N. So I'll write it as N naught plus delta N. That's number 2. N naught plus delta N, by which I mean that 10 power 15, the equilibrium density, plus 10 power 16, which is the excess minority carriers or excess electron hole pairs that I'm creating in the lattice, right? 10 power 16 per second. So that way. Okay. So similarly, so what will this be? This is going to be 1.1, right? 1.1 into 10 power 16. Okay. Similarly, what will be the P, the total hole density? It will be the equilibrium density P naught plus delta P. In this case, the equilibrium density was 10 power 5 plus delta P was 10 power 16. So this is going to be equal to 10 power 16. So what you notice, by choosing my external stimulus, I am able to create much more, a lot of minority carriers. Okay. Of course, this depends on the rate at which you're generating. But let's do the NP product. What is it? Now, NP product is going to be 1.1 into 10 power 16 times 10 power 16. That turns out to be equal to 1.1 into 10 power 32, which is much, much greater than Ni, right? So basically, this implies that say non-equilibrium situation, non-equilibrium condition. So what if you have non-equilibrium? What happens? Then you have non-equilibrium. Well, to understand that, let's see. You turned off light. We switched on. We created this. Okay, we have the steady state, and we created a carrier density this way. N and P have changed. Now you turn off the light. What would happen? So then you have these excess electrons and hole pairs. So they will recombine. Right? We talked about it multiple times. So essentially, an electron and hole, when they occur at the same position in the lattice, when they come into the same position, then they can annihilate. Electron hole pair can be annihilated. So if you turn off light, essentially what's going to happen? Your electron density, which was, let me write it in red itself, n was equal to 10 power, 1.1 into 10 power 16. It should eventually go back to equilibrium, right? Because the excess electron hole pairs will recombine. So it will go back to equilibrium. So this becomes, equilibrium was 10 power 15, right? And similarly, P should become, it started out with 10 power 16, and that should become 10 power 5, right? So it should go back to equilibrium. So the driving force or the stimulus which was creating excess electron hole pairs is the light in this case, in this example. So when we have that, we have these excess carriers, but once the light is removed, they have to go back to equilibrium, right? So I'll ask you a very important question that I need you to pay attention to. So think about which carriers, majority or minority, okay, determine the rate of recombination. Okay, what determines this? You saw that when you have a perturbation, let's say external stimulus, which is perturbing the electron hole densities, you saw that the majority carriers are not significantly affected, but minority carriers are significantly affected. Of course, depending on the strength of the perturbation. Okay, but when will the electron hole pairs recombine? When you have sufficient number of electrons and holes. In this case, what happens is your delta n is only going to change from 10 power 16 to 10 power 15, not a whole lot, one order of change, right? But delta p will change over, now in this case, 10 power 16 to 10 power 5, 11 orders of magnitude change. So what happens is, let's say, initially you started out with delta p of, let's say, equal to 10 power 16 at t equal to 0. Okay, you started out that. And after a certain time t naught, it might have become 10 power, let's say, 10. Okay, after at t equal to t naught. And then after very long time, we will define what this very long time is. It's going to become 10 power 5. Let's say this is going to be t equal to infinity. Just as an example. It's not going to be really infinity. We're going to get, we'll see some examples. Okay, what this is meaning is the rate at which the recombination happens is proportional to the minority carrier density. Okay, so once you have a very high minority carrier density, excess minority carrier density, then the rate of recombination is going to be large and it's going to decay very, very fast. But once the number of the minority carriers, excess minority carriers comes down, then the rate of recombination slows down. Okay, and this is an important thing. So we will make a very important conclusion here. We'll say that minority carrier concentration determines non-equilibrium dynamics. Because you see that always there are sufficient number of majority carriers present. We don't have to worry about the availability of majority carriers. The rate of recombination is going to be purely determined by the minority carriers. Okay, so that's why we conclude this. All right. Okay. So now let's take one more step forward. Okay. What I'll do is I'll just quickly, summarize some definitions that we will be using. You're already familiar with N naught and P naught and N and P. N naught, P naught are the electron and hole concentrations at thermal equilibrium. N and P are the total electron and hole concentrations. Okay, so you see that N naught and P naught are going to be essentially independent of time. These are independent of time and most often position, because if most of the time we will talk of uniform doping. Whenever you have uniform doping, your equilibrium concentration is going to be uniform. Okay, whenever you have uniform doping, okay, this position independent of position. All right. So now what I'll do is I have this total electron concentrations and I'll define excess minority carrier concentration as delta N and delta P. Okay. So the change from the concentrations. Okay. So these two quantities, N and P and delta N, delta P, let me put it in black. So, okay. These two quantities are going to be, they depend on time and or, I mean, it could even depend on time and position or one of them. Okay. So it depends on, what particular excitation we have and where the excitation is located. Okay. So that will give you, these are functions of time and position. And then there are Gn and Gp, which we are essentially calling the excess electron and hole generation rates. Okay. So how many carriers are being created per second, sort of. And the last important quantity that I want you to pay attention to is the excess minority carrier lifetimes. Okay. So basically this means this is essentially time between recombination events. Okay. So you have plenty of electron hole pairs present, right? But it's going to take a certain amount of time for them to recombine. Okay. So how many events per, how many recombinations per unit time? And you just look at what is the average time between recombination events. Okay, that is excess minority carrier, minority carrier lifetime. Okay, what this means is, okay, we could try to plot it, just as a, now we will see it again, but just for now to give you an idea, let's say I have a semiconductor and I have excess minority, somehow I introduced minority carriers, okay. So I introduced, let's say delta P, okay, I'm plotting only excess, this is delta P and this is delta P naught. At time t equal to 0, I have a delta P naught, which is introduced. Well, okay, to maintain convention, let me take it as a small delta, okay. So this will be your delta P and this will be delta P naught, okay. So we created that at time t equal to 0. This is time t equal to 0 and this is time t, this is time, right? So how will the excess minority carrier density, okay, by the way, here I'm talking of delta P, that means I'm taking an N-type semiconductor, okay, because delta P for a P-type semiconductor doesn't really play a role because it's a majority carrier density. Excess majority carrier density doesn't play much of a role. But if you are talking about minority carrier density, that is important. Okay, so you introduce somehow and then you remove the stimulus, then it's going to come back, right? It's going to take some function. Right now you don't know what that function is, but towards the end you will see that this is an exponential function. Towards the end of this lecture you will see this. So essentially the time required, this is going to be some time, right? This is tau, which is basically tau P, which is the excess minority carrier recombination time. So how much time does it require for the density to fall to 1 over E value? Okay. We will actually solve it and show you this in the end of the lecture today. Okay, so these are the definitions.